topic of this video is about covariance and correlation. There are 4 parts in this video: covariance, correlation, the compare of these two measures, and the exercise. Firstly, I will introduce the covariance. So, what is covariance? In probability theory and statistics, covariance is a measure of how much two random variables change together. If the greater values of one variable mainly correspond with the greater values of the other variable, and the same holds for the smaller values, the variable tend to show similar behavior. The covariance is positive. In the opposite case, when the greater values of one variable mainly correspond to smaller values of the other, the variables tend to show opposite behavior. The covariance is negative. The sign of the covariance therefore shows the tendency in the linear relationship between the variables. The magnitude of the covariance is not easy to interpret. It means that the value of the covariance only can show what tendency is, but how strong the tendency is cannot be only reflected by the value of the covariance. The covariance can be defined as the equation below, and it can simplified as EXY minus EXEY. So if XY are two independent random variables, EXY will equal EXEY, and the covariance XY will be 0. But on the contrary, when covariance XY equals 0, we cannot conclude that the XY are two independent random variables, and the variance of x plus or minus y equals the variance of x plus the variance of y plus or minus the covariance of xy. This is the relationship between the variance and the covariance. And there are some other rules about calculating the covariance. You can have a look. The proof of these rules are very simple, so I will not spend more time on this. Let's come into the next question. What are the applications of covariance? There are 3 applications. Covariance is an important measure in biology. Certain sequences of DNA are conserved more than others among species, and thus to study secondary and tertiary structures of proteins or of RNA structures, sequences are compared in closely related species. If sequence changes are found or no changes at all are found in non-coding RNA, such as microRNA, sequences are found to be necessary for common structure motifs, such as an RNA loop. Secondly, covariance plays a key role in financial economics, especially in portfolio theory and in the capital assets pricing model. Covariance among various assets returns is used to determine, under certain assumptions, the relative amounts of different assets the investor should or are predicted to choose to hold in a context of diversification. Thirdly, the covariance matrix is important in estimating the initial conditions required for running weather forecast models. And the second part, correlation. Correlation is a statistical measure of how two variables move in relation to each other. And the correlation is usually computed into what is mostly known as correlation coefficient, which ranges between -1 and 1. And the correlation coefficient have the same relationship as the covariance. It means that the positive correlation coefficient represents similar behavior of random variables. In the opposite case, it is also true. The closer the correlation coefficient approach -1 or +1, the stronger relationship between two variables. And the correlation coefficient can be defined as the equation below. The correlation coefficient of xy equals the covariance xy over sigma x, sigma y. This sigma x and y represent the standard deviation of two variables. There are 3 special situations should be mentioned: no correlation, perfect correlation, and perfect negative correlation, in which the correlation coefficient equals 0, 1, -1, and the relationship of xy in these three cases can be simplified expressed as three figures on the right side. And part 3. The compare of two measures in probability theory and statistics. The mathematical concepts of covariance and correlation are very similar. Both describe the degree to which two random variables or sets of random variables tend to deviate from their expected values in similar ways. Obviously, they also have difference. As we have mentioned in part 1, the magnitude of the covariance is not easy to interpret. Covariance only can show us what tendency these two variables have, but the correlation coefficient not only can show us the tendency, but also make the trend strength quantified. The value of correlation coefficient can show the strength. This is the difference between covariance and correlation. And part 4. There are two exercises to show how we can calculate the covariance and the correlation coefficient of different functions. Exercise 1. Exercise 1 shows us how we can calculate the covariance and correlation coefficient of continuous random variables. For function xy equals x plus y, we can use this joint function to calculate the expectation of x and the variance of x. Similarly, we can also calculate the expectation of y and the variance of it. Therefore, the covariance xy equals expectation of xy minus expectation of x and expectation of y equals negative 1 over 144. And finally, we can calculate the correlation coefficient of xy equals negative 1 over 11. 2 is an example to show how we can calculate the correlation coefficient and covariance of discrete random variables. And it is also an example of uncorrelated but dependent random variables. We can use the data to calculate the covariance of xy equals 0, so the correlation coefficient also equals 0. It means that the xy are uncorrelated. However, we can easily find that the xy are not independent. So if two random variables are uncorrelated, it doesn't mean that they are independent. And these are the reference of material used in this video. And thanks for your watching. The topic